So, as we are considering more exam questions, we have got another question that we are going to work on from our August 2024 exam. On our transformers, we are given on question number 3, guys, that was 3.1. Explain why a transformer is rated in kVA, not in kilowatts. Why do we use the kVA? So it is because of the losses that we have, guys, that the copper loss of a transformer depends on current. The iron loss depends on what? On voltage. So those are the two that we are actually going to be working with. So that's 3.1, the copper loss. Remember that. The copper losses of a transformer, which is the copper loss of a transformer depends. So this one, it depends on what? On current. Whilst the other part of the iron loss depends on what? On voltage. So, and iron loss on what? On voltage. It depends on what? On voltage, this one. So if we take a closer look, when we are calculating the total transformer loss, when you are calculating the total loss, whenever you're working with the total transformer loss, it depends on the volt ampere and not the phase angle between the voltage and what? And current. So that is why. So you're going to have this one, the total transformer loss. The total transformer loss depends. So it depends on the what? On the volt ampere. So this one, it depends on the volt ampere, which is voltage ampere, volt ampere. And not on the phase angle between what? Voltage and current. All right. And not on the what? On the phase angle. On the phase angle between what? Between voltage and current. So remember the part of the phase angle that we have between voltage and current is the one that will give us power. The moment we use that one, you'll be calculating power. But we are saying it does not depend on that one. The moment we use like this, cos phi, where this is the phase angle between voltage and current, it means we are now calculating the true power. But in this case, we are saying it does not depend on that part. It is just voltage and current. That is why we consider voltage ampere. That is the why we end up with the kilovolt amperes. So if you are given, guys, volt ampere, you can divide by 1000. You have what? The kilovolt ampere. That is the case. State two constant losses occurring in a transformer on 3.2. So the constant losses, we understand these are all ion losses. All ion losses. So if I talk about all the ion losses in that case, it means we are simply going to talk about the hysteresis. So there we have got the hysteresis losses. We also have the eddy current. All right. We also have the eddy current losses. We also consider the dielectric. This is the condition. We also have consider the dielectric losses, all ion losses that we have. That is the consideration. All right. So any two there, remember this, just say two. Then on question 3.3, let's see for 7 marks, what is it that you are given here? They are saying it's a 250 kVA single phase transformer, 50 hertz, this and that. All right. So that is our, we are given our S250 kVA working at a unity power factor. So at a unity power factor, that means our cos phi is going to be 1. Here's an efficiency of 95%. Efficiency is 95%, but it does not end there. They are saying at both here. This is the most important part. at both half load and full load. The efficiency that we are seeing here is the same at both half and what? Full load. At both half load and full load. So this is the most important part. It is the same. All right, so no problem. Let's see. 3.31, calculate the iron loss and the full load copper loss. Remember, when you are referring to this part of the iron loss, iron, this is the what? Our open circuit, the iron loss. We talked about this, guys, on the introduction. This is our open circuit. Full load copper loss. This is our short circuit. So they want you to calculate open circuit and short circuit power. From where? So let's consider, guys, that they gave us efficiency. We are supposed to analyze our information. They gave us what? Efficiency. Remember our efficiency formula. I talked about this, that it is just a matter of the factor of full load that is affecting. To say it is at half load, another one, it is at this, but the same efficiency. So the factor there is being that is affected. In our case, we are working with a condition where we are at full load. So our K is supposed to be 1, and at half load, which is 0.5. Those are the effects that we have on our K. But the efficiency formula, guys, it is not going to change this one. It is going to be the same. Our efficiency formula is going to be the same. On our efficiency formula, we can see properly that the open circuit is there, the short circuit is there on our formula. So let's take our formula and put it into consideration and see what's going to happen by substituting. Definitely there is going to be solving of equations. The way that we see them, it's going to be solving of equations because we have to substitute our values that we are given, and there are two unknown values at the same time. Two unknown values. All right, we saw that efficiency is equal to, that's Ks cos phi over, this is going to be Ks cos phi plus open circuit plus K squared short circuit times 100%. So that's times 100%. So this is what we are given, and we have got everything else. Everything is there. We need this open circuit, short circuit. So K depends on the type of the load, and it's a unity power factor. So you're just going to use a 1. Everything is there. And also, take note, there's 100% on your formula. So you can even remove this 100%. If you divide by 100%, it means you are removing it. So you can even divide this. It will give us 0.95. That means we are not going to use a percentage if we use it as a decimal like this, all right? So this is it. The efficiency is the same, but the different type of loads that we are given, there are two types. So let's start with the half load, all right? Because we are saying these, they have the same efficiency. So let's start with the condition for half load. For a half load, what will be the condition of our efficiency for the half load? Efficiency is equal to what? The same thing, 95%, which I said as a decimal, 0.95. So for the half load, 0.95 is equal to what? Let us substitute. Our K is what? At half load, it means our K will be equal to what? Will be equal to 0.5, half. The K is the one that is affected. 50%. That is 50 over 100, which is what? Which is 0.5. So that will be 0.5 times our S, 250. So take note here. I'm using this in kilo values. Kilo values. The value that I'm using is kilovolt amperes. So it means this P and this P that I'm having, they will be in kilo also. Whatever that I'm going to get here, guys, must be in kilowatts because I used the kilo. If you convert this to 1,000, like you multiply by 1,000, it means your answers are not in kilowatts. You are the one who is supposed to convert if you want, or just have to leave it like that. All right, so that's it, guys, for a unity power factor. That's a 1. All right, that's over what? This part here is simply a repetition that you're going to have here, this one. So that's 0, 0.5 times 250 times 1 plus, we do not have the open second, this one. All right, our K, remember, it's what? 0, 0.5. So that's plus 0, 0.5 squared. 0, 0.5 squared P short circuit, like that. So that's an equation that we have formed. And on this equation, we have got two unknown values in one equation, this one and this one. So we are going to definitely have two equations so that we solve them simultaneously. All right, so this is it, guys. You can simply solve it this way. This is a fraction, make it over 1 like this. So you can cross multiply. This multiplies this side, this multiplies this side. But take note, as you multiply by this 0, 0.95, guys, it is going to multiply everything here. Here, it multiplies everything like a bracket like this. So it's 0, 0.95 times this, 0, 0.95 times this, 0, 0.95 times this. It is going to multiply everything. Take note, you are expanding just like a bracket. Okay, so that's 0, 0.95 times this whole part. If you multiply 0, 0.95 times the whole of this part, you are going to get 118.75. 0, 0.95 times this, it was going to be plus 0, 0.95 P out. 0, 0.95 times this, 0, 0.5. It was going to give us a decimal of 0, 0.2375. So I'm not going to round off here because this is what I'm having as it is. All right, that's P short circuit. We are done. 0, 0.95 multiplied everything. So this is equal to, you cross multiply 1 times across the equal sign there. That's we are going to multiply everything. It was going to give us 125. That's 125. So as you can see, these are unknown values. P and these are unknown values. So you can transpose this to the other side, subtract it. It was a positive, so it's going to be a negative here. So you're going to subtract this. So we are going to remain with this part. That's 0, 0.95 P out plus 0, 0.2375 P short circuit like this, which is equal to what? Subtract these two, that was going to give us 6.25. So if we subtract this, it was going to be 6.25. That is the difference between 125 and what? And 118.75. So with this, we can even reduce our equation. As we can see here, we can even just leave it like that. It's up to you. You can reduce this one. Just try to reduce by 0, 0.95 each and every part. You can choose to reduce by this one. It's in your hands, but as for me, I'm just gonna use 0, 0.95. I'm just gonna use 0, 0.95 throughout. 0, 0.95 throughout. So dividing by 0, 0.95 cancels this. That's P open circuit plus divide these two. It was going to be 0, 0.25. So you're going to get 0, 0.25 P short circuit is equal to, you divide these two, it was going to be 6.579. All right, so that's an equation that you have formed. This one, we can call it equation 1. Let's just see what's going to happen. Let's leave it like this and see if there can be any adjustments after. There can be adjustments after. So this is at what? At half load. You formed an equation at half load. With the same situation that we had here, you're going to apply it at full load. Same part, but at what? At full load. Remember, they gave us a condition that the efficiency is the same at both half and full load. So what was going to be the condition when it was at what? At full load. What was going to be the condition? The condition lies on K. The K that we are going to use at full load is 1. The full load, remember, this is the blast part that we have. So K will be what? K will be 1 there. So at full load, we know that K is what? K is 1. So when K is equal to 1, we are going to substitute just like the previous case on this formula that we had. So we are going to have our efficiency. Remember, efficiency 0.95 is equal to what? The part of K is going to be, this is the only part that is going to change where K is. So it's going to be 1 there. Everything is going to remain as it is. So that's 1 times 250 times, remember, the unity power factor. We had a unity power factor, remember. This part, it remains as it is, plus the open circuit plus K squared. Remember, this is K squared, but we are working with the K as what? As 1. 1 squared, guys. It's just 1, guys. 1 squared is just what? It is just 1. So this is it. Just like the previous case, this is the same as over 1. So you're going to cross multiply. So take note, 0.95 multiplies everything here. So it's 0.95 times this, 0.95 times this, 0.95 times this. All right. So let's cross multiply 0.95 times this bracket. It was going to give us 237.5. 0.95 times P open. It was gonna be 0.95 P open. 0.95 times this. 1 squared is 1. So if you multiply by 0.95, it was gonna be 0.95 P short circuit. Then you cross multiply this, multiplies everything here on top. So this is 250. Just like that. So with this, we can simplify our equations. Let's simplify this equation further. Let's take this to the other side. So definitely it was going to be a negative because it's a positive here. So it crosses the equal sign. It was going to be a negative there. Okay, let's hope it is not going to affect my board, guys. Let's see this part. So it was going to be a negative. Okay. It has already affected my board. All right. So there we got affected. So you see, guys, these boards, I don't know. Let's just hope it to be fine as we are working with our revisions. But yeah, guys, I can't do anything because I'm just using something that is now saved. So guys, just try to understand also as you are revising there to say, guys, these softwares, software is a device. Is it a device? No, it's not a device. It's something that you don't even understand. But anyways, we just hope we're gonna work with because the information that you'll be having, guys, that's another thing. Like if you're working with more information, like you see these technical subjects, if a lot of presentations, this so the board even get confused. Uh, but it's okay. So you're gonna take this to the other side. Then it was gonna be a negative 237.5. So there being a negative, we subtract. That was going to be 12.5. Okay, yeah, that's 12.5 there. So this was gonna be 12.5. So with the this equation that we have, this is our equation 2. Remember, we are calculating this from the full load. But we can even reduce just like the previous case, 0.95, 0.95, guys. We can even reduce by that. 0.95 here, 0.95 here, 0.95 here. So this was going to cancel. So P open plus this was going to cancel. We got P short circuit is equal to, you divide these two, that was going to give us 13,158. Guys, let it not start again. It's not supposed to do that again. All right, let's hope it's not going to do that again. So this is it. We have this as our equation 2. All right, so we're going to have this as our equation 2. So this is it, guys. You just form equations like at half load, because the efficiency is the same. So that efficiency is the same efficiency that you use here. At what? At full load. So the only thing that has changed is that at half load, K is what? 0.5. Here, K is what? K is 1 at full load. Just like that, this question, it will be repetitions. They will repeat these questions, guys. Just answer this way. Then this is the one. On solving of the equations, I do not want to limit you here. It is in your hands here to solve. These are simultaneous equations. Are you going to use elimination method? Are you going to use substitution method? Which method are you going to use? What we want is to know this value for the open and for the short circuit as our answers. All right. So as for me, I was just going to do this way, guys, because I can see that these two are the same. These two are the same. This one, P open, and this one, P open here. We do not have like anything that is affecting. So yes, I can use substitution methods and that. But here I can just make it the subject both ways. From equation one, I have to finish equation one. There, P open is equal to what? All right. So this is it. Take this to the other side. It will be a negative there. So it was going to be 6,579 minus 0,2 P short circuit like this. So this is what you have, okay? Then we also do the same thing on this one. We take the short circuit to the other side. So it means P open was going to be 13,158 minus, okay? Take note, this is plus. So the moment we take it to the other side, it was going to be what? A negative. Oh, guys, let me just try to increase this one a little bit. All right, something like this. So this is it. This is our equation one, guys. All right, this is our equation two. We wrote it in terms of what? In terms of the open circuit. This one, open circuit here. This is open circuit here. So what does it mean? It simply means also the remaining part here. This one, this part of our right hand side. This one must be equal to this one also. These two must be equal also. Guys, there's no way that we can say this is open circuit. Our answer is 3. Then they are open circuit. Our answer is 4. It cannot be like that. They have the same answer here. So it means also that can work. If they numerically, if they are the same numerically, they are the same numerically. It means also in terms of expressions like this, they are supposed to be also equal. There's no way we can say our open circuit here is 3, then 3 kilowatts. Then here we are saying it's 4 kilowatts. No, guys, it is the same. So if it is the same as a number, which is 3, let it be the same thing when we see these letters, like when it is given in terms of another letter as an equation like this. Guys, this is our mathematics N4. So in fact, N3, just try to go back to N1, N2, like how to solve those simultaneous equations. Because you'll be revising question papers, guys. You see a method here. They put another method. Then you think that it's a follow-up method. No, it's not a follow-up method. They are just using it's like it's someone like you guys who is even creating the memo there. Someone like me, I just create, okay, this time I want to use elimination method. So you are focusing on elimination method because you saw it from a certain question paper. It is not like that. You use any as long you're solving what? Simultaneous equations. So this method that I'm using here to find PO and equate that one, I can choose to use another way in another explanation. It is up to you. Guys, revise your simultaneous equations. Yeah, I just saw that it is easier because of this. It is easier. I don't need to divide by anything. So I'm just going to equate these two. So if we equate definitely PO to PO, this one, and this one, it will be 6,579 minus 0,25 P short circuit, which is equal to this one that we had on this other side, 158. Okay, so am I getting 158? 13,158. 13,158 like this minus P short. So as you can see, these two are the ones that are the same. So you can solve for this by transposing. You can take this to the other side. It's going to be a positive there. So it will be negative 0.25 P short circuit plus P short circuit, this one, it will be positive. If you take this to the other side, it will be a negative. So it will be 13,158 minus 6,579 like this. So this is the case that we are going to have. This is just simplification. Here it's 1, same as 1. Remember your algebraic expression. So you're going to add these two, minus 0.25 plus 1, which was going to give us 0.75 P short circuit like this. Then you subtract this side. That was going to give us 6,579 like this. Okay, then simply divide, guys, since this is a multiplication. 0.75 both sides, 0.75 both sides. So this was gonna cancel, and we have our short circuit, which is what? This was gonna be 6,579. So this is where our units now are important, guys. After dividing this one and this one, it is going to be 8,772. All right, after dividing this one to this one. So this is where our units now are important. I'm going to write the units, but I want you to see something before I write those units there. The units, you work with what you had, because you want to know, is it just going to be watts, or I'm going to write it as kilowatts? It is because of the value that we substituted here for our S there. We substituted kilovolt amperes, kilovolt amperes, kilo. It was in kilo. So I said, if it is like that, your open circuit, short circuit, they will be in what? In kilowatts. So it means, guys, we are in kilo. The units that we are using there will be kilo. We know the units for power, watts, but kilowatt, kilowatts. So this is automatically in kilowatts, not only the watts, but kilo. Take note because of what you substituted. So this is it, guys. Remember, that is our full load. If you are calculating the short circuit, you are calculating what? The full load copper loss. The full load copper loss. So they want to confuse you in exam. They want to confuse you, guys. Calculate the full load copper loss. What is that? Calculate the iron loss. So the iron loss can be calculated, which is what? Our P open. Remember, we said P open represents our iron loss. So we can calculate either from this one that we made the subject here. We can calculate from this one that we made the subject here. Anyone. We can calculate from this one. Anyone can give us what? The open circuit there. So our open circuit was going to be what? So for the open circuit, since our open circuit is equal to this, it was going to be 6,579 minus 0.25 times short circuit. Remember, we calculated and got 8,772. We are just substituting the value that we got here for the short circuit, the one that we just calculated now, 8,772 in kilowatts. In kilowatts. So if it is in kilowatts, it means also our open circuit, the one that we are calculating now, is also in kilowatts. So that's 4.386 kilowatts. So that was it for our iron losses. So that is for the iron loss. This is what you're going to have. Okay, so guys, questions can be like that. They will be like, they want you to understand the basics. Do you actually understand where all this information was taken from? So these values, guys, our open circuit and our short circuit, I want you to remember those values because we're going to need them. Remember, guys, look at my board. It will start again to misbehave just like the previous time. So I want you to remember those values. As for me, I'm just going to take my values and substitute here. They want us to calculate now the efficiency on 3.32, the efficiency. Remember your efficiency formula is just a matter of substituting, of which I already erased it here. So let me just do it this way, guys, so that we do not get rid of our formula there. All right, sorry for that. So now our question was to calculate this efficiency, but they are saying at 70%. At what? 70%. It is at 70% full load, 0.8 power factor lagging. All right, so our power factor, it's 0.8, which is our cos phi there, 0.8. Then we have what? The efficiency at what? 70% of full load. 70%, that's our K, will be 70 over 100. Remove that percentage, 70 over 100, which is what? 0.7. So that is the case. All these guys, we have them. We calculated this, so we're going to just substitute the values that we calculated as they are. So that's 3.32. So that's our efficiency, guys. So K, remember, we are working with this condition, guys, 70%. So that's 0.7 times S, 250 kilovolt amperes times 0.8, our power factor. So I used the kilovolt amperes. It means I must use this open circuit in what? In kilowatts. And also the short circuit in kilowatts. I'm going to repeat that part now and again. And there we need now we're going to, okay, I remember there I removed that 100% because of the calculations that we had. Now we're going to put that back. We need that back, guys. All right. So let's repeat this. Okay. Okay. That's 250 times 0.8 plus our open circuit, the one that we calculated. I erased those ones, but we calculated these ones, guys. Remember, I told you must remember those values. The open circuit, remember, it was what? 4,386 kilowatts. It was in kilowatts, this one. So we already calculated this. Then K squared plus K squared, our K squared, 0.7 squared times what? The short circuit, we also calculated our short circuit. Remember, it was 8.772 in kilowatts also. So it must be in kilo. If you choose to use the kilo in the first place, maintain that throughout. Must maintain that throughout. So as a percentage, multiply to 100%. That was going to give us the efficiency of our transformer at what? 70% of the full load. And that was going to be 94,159 if you multiply properly on your calculator. 94,159 percent. So this is how typical questions actually might be given as we can see, this is an exam question. So typical questions, guys, might be given as this. So make sure you do work out as many questions as you can. The comment section is there to communicate. If there is a question paper maybe that you feel like we can work on that is still having some challenges in your electrotechnics N6, let us communicate, guys. The comment section is there so that you can communicate. But this is how our questions might be given as. So it was easy, guys. Just form your equations. You are done.